Hi, let's continue with our session. In this video, I want to talk about hyperparameter tuning, which I can optimize. So in machine learning, a hyperparameter is a parameter whose value is set before the training process begins. So for example, I think it's important to note. So hyperparameter is a parameter whose value is set before the training process begins. So for example, the choice of learning rate of a gradient boosting model and the size of the hidden layer of a multi-layer perceptron are both examples of hyperparameters. So by contrast, the values of all the parameters are derived via training. Hyperparameter selection is important because it can have a huge effect on the model performance. So let's write some note for that. The choice of a gradient boosting and model and the size of the hidden layer of a multi-layer perceptron are example of hyperparameters. So hyperparameter selection is important because it can have a huge effect on the model's performance. So the most basic approach to the hyperparameter tuning is called sklearn. So the most basic approach for hyperparameter tuning is research. So in this method, you specify a range of potential values for each hyperparameter and then try them out on until you find the best combination. So in this method, you specify a range of potential values for each hyperparameter and then try them on out until you find the best combination. So the brute force approach is comprehensive but computationally intensive. More sophisticated methods exist. So in this video, we will learn how to use Bayesian optimization over hyperparameters using the scikit-optimize. So in this video, you will learn how to use Bayesian optimization over hyperparameter using scikit-optimize. So in contrast to a basic research, in Bayesian optimization, not all parameters values are tried out, but rather a fixed number of parameter setting is sampled from specified distribution. So let's write in Bayesian optimization. Not all parameter values are tried out, but rather a fixed number of parameter setting is sampled from a specified distributions. So now is the time to write some code for that. So after all the node is written, so we'll load the Y dataset from sklearn. So in here we'll from sklearn import datasets, and then we'll have is Y underscore data set equal data set dot load underscore Y. So we have is x equal Y underscore data set dot data, and we have Y equal Y underscore data set dot target. Now let's run the cell. So let's wait for it to have the connection. So this is a short one, so we don't need to use the GPU. So now the second step is we need to import XGBoost and stratify K4. So we'll import XGBoost as XGB, and now we will just from sklearn dot model underscore selection we'll import straight K4. So let's run the cell. So we don't have any error, and now we will import Bayes search CV from scikit optimize and specify the number of parameter setting to test. So we'll use from skop import Bayes search CV, and now we'll set the number of iteration is equal to 50. And now let's run the cell. So we don't have the modules and scope. So what will you do in here? We just pip install. So let's run. So the last time we did have the error in here, which is from scope import PSS. So we have the error in here. So I actually go to the scope base with the scikit-learn library here. And what I do is I just use their code in here. So from scope.base search CV, and then I just copy and then paste here. So this is a library that we need. And now we should fix the error. So what we will do, we will use pip install as scikit optimize. So we need to install that one because it doesn't have in Google Colab. And now there will be no errors. So we need to specify the estimator. So in this case, we select XGBoost and set it to be able to perform multi-class classification. So now we have is estimator equal xgb dot xgb classifier, and now we have n underscore jobs equal to -1, comma objective is equal to multi softmax, comma, and we have is eval underscore metric equal mirror, comma, and we have is the velocity equal to 0, comma, and then we got num underscore class equal len set y, comma. So we need to specify a parameter search space. So let's run that, and we need to specify a parameter search space. So we need to have a search underscore space equal open bracket. So we have the learning underscore rate is equal to, it should be that one. So 0.01 comma 1.0 comma log uniform, and then we have comma, and now we have mean child weight 1 comma 0 comma 10, and now we got is max depth, and then we got 1 comma 50 comma max delta step is 0 comma 10. So sample we got is 0.01 1.0, and then we got is uniform, comma, and now we got is sample underscore by 3. So we wait is 0.01 comma 1.0 comma log uniform. So I just copy this one. So co-sample by level. It will be the I just copy 0.011.0 uniform, log uniform, and then we got break lambda is 1e negative 9 comma 1000 and then comma log uniform, and then we got break underscore alpha. So it will be similar. So 1e 1.0 and then log uniform, and the next one is gamma 1e negative 5 negative 9 0.5 log uniform, and then we got is mean underscore child underscore weight, which will be 0.5 0 comma 5 comma, and then we got n underscore estimators, which will be 5 comma 5000, and now we have is scale both weight is equal to 1e negative 6 500 and then comma log uniform and then comma. So I don't have any, I hope I don't have any mistake, and we did successfully specify a parameter for search space, and now we need to specify the types of cross validation to perform. So we need to specify the type of cross validation to perform. So we have CV equal stratify K4. We have n underscore split equal 3. And then we have shuffle equal true. And now we will define AS search CV using the setting we have defined. So we have is bias underscore CV underscore tuner bias tuner equal bias search CV open bracket, and now you have is estimator equal estimator comma search space equal search space equal search space scoring equal accuracy comma cv equal cv comma and underscore jobs equal -1 comma and underscore ether equal and underscore iterations comma we got verb post is equal 0 comma refit equal true comma verb post Hi, let's continue with our section, and in this video we'll continue what we have done so far. So we'll define a callback function. So we need to import pandas as PD. We need to import numpy as np, and we need to define the function called bring underscore status, which will take the optimal underscore results. So let's write a comment here. So we need to show the best parameter found and accuracy attained of the search so far. So we will need to create a model underscore tested equal bd dot data frame. So we have a bias cv tuner dot cv underscore results underscore, and now we have a space underscore parameters underscore so far equal pd dot series. We have is by s cv tuner dot base params, and now we will bring is the model slash and best accuracy so far, and then we got empty bracket slash and that means you go down for one line, and then we'll have a space best parameters so far semicolon of open brackets close brackets, and then dash and dot format. So this will be a very long code. So we have its length. We will take the models underscore test comma np dot round. So it will round up the number. So we will round to 3 decimals. So we have by s cv tuner dot base score 3. So we will round up to 3 decimal points. And now finally we will have is by s cv tuner dot paste params comma, and now we will have is clf. So we have a clf dot underscore type equal by s cv tuner dot estimator dot underscore class underscore dot underscore name underscore, and now we have model dot underscore so models underscore tested dot to underscore csv. So we have a clf underscore type plus underscore cv underscore results underscore summary dot csv. So after we got that, we'll write to our csv file. So let's run the cell. I hope there aren't any errors, and we got the error. So best param bs cv tuner dot best underscore param underscore. So I did rewrite the code and I did fix the error. So and now I did successfully run, and it's write to the CSV file. So this is a file that we will have to write it. So it will store in Google Colab, of course. And now we will perform the parameter search. So we will have is result equal ps cv tuner dot fit. So we have is x comma y comma callback equal ring status. Let's run. So there is need to have a space in here. So I did fix the error, and we need to change to number of iteration to 50 to 9 because 50 is too much. So it will go down to 0, and the code sample by level it will go down to 0, and this gamma is go to 0 below 0. So that's why there is an error. So it's okay if you can get the, because we just have 9 models, so we can compare them. So our best accuracy is model 9. It's around 0.93538. That is very good. 983. So that is a very good model. So this is very consistent for model 5, model 6, model 4 to model 9 is 0.983, and you feel free to change the number of iterations to 10 or maybe 15 or maybe 3, 4, 5. So that is not really important. So now we need to explain how does it work. So let's explain is how does it work. So in step 1 and 2, we did import a standard data set, the Y data set, as well as the library needed for classification. So in which we specify how long we would like the hyperparameter search to be. So in terms of a number of combinations of parameters to try. So the longer the search, the better the result. So the longer the search, the better the results. So the risk of overfitting and extending the computational time. So in step 4, we select the XGBoost model and then specify the number of classes, the type of problems, and the evaluation matrix. So now let's write step 3 first. So in step 3, we did specify how long we would like the search to be. So this could be here, the longer the search, the better the result. So I should bold this text because it's really important. So I need to bold it because this is very important. And in step 4, we did select XGBoost as the model and specify the number of classes, the type of problem, and the evaluation matrix. So now in step 5, we did specify the probability distribution over each parameter that we will be exploring. So this is one of the advantages of using Bayes search tree over a simple grid search, as it allows to explore the parameter space more intelligently. So step 6, we specify our cross validation scheme. So since we are performing a classification problem, it makes sense to specify a stratified fold. However, for a regression problem, stratified fold should be replaced with k-fold. So we did use stratified fold, and for a regression problem, it will be so stratified fold will be replaced with k-fold. So also note that the larger splitting number is preferred for the purpose of measuring results, though it will come at a computational price. And now in step 7, we can see additional settings that can be changed So in particular, number of jobs allows you to parallelize the task. So n underscore jobs allows you to parallelize the task. So the verbosity and the methods used for scoring can be altered as well. So to monitor the search process and the performance of our hyperparameter tuning, we define a callback function to bring out the progress, which is in step A. So step A, we did define a callback function to bring out the progress. So the result of the research are also saved in the CSV file. And finally, we run the hyperparameter search in step 9. So step 9, we did run the hyperparameter search. So, and that is all in this video. So I hope you enjoy our small projects, and I will see you in the next video.